Hello, everybody. My name is Alex Kehayias, and welcome to my talk about functional game engine design for the web. So we have two talks that are going to happen. One, which is going to be more focused on how you actually design and implement a functional game engine. And then Bryce Covert is also going to be giving a talk about specifics of solving problems in actually implementing an adventure game in Clojure. So before we begin, I just want to talk about where this all comes from. So I, like many of you guys, have spent several years building back-end systems with Clojure, having to deal with very large data sets, lots of plumbing, lots of ETL, sticking things in the right places. And there's a lot of things that I've learned along the way about data-oriented design and solving problems with data in Clojure, and using some of those ideas now to apply it to something that I have as a pet project, which is games and game engines as a result. So to start off, what is a game? How do I actually define what a game is? And really, it's actually state. So one of our most feared but also most revered things about anything related to a program is actually state. And in games, we can think about it as state transitions that are happening 60 times per second. They tend to be pretty complicated. It's a multimedia interactive experience that has lots of moving parts. And a lot of times, the moving parts tend to be intertwined. So there's some complexity inherent in building and expressing games. So if I were to sum all of that stuff up, I would basically put it into this one chart, which is state and time, or to borrow something from the physics world, state time. So as we can see, each box is a state at any particular point in time, and we're always moving linearly across time. So don't think about it as like minutes, seconds, or hours. Think about it as like ticks that are always moving forward and progressing. And the state of the game world is what it is at any particular point in time is the truth. So just a quick justification, why would we even want another game engine? Aren't there plenty of other options? And of course, there are a quick shout out to the people who are working on Arcadia on top of the Clojure CLR. Timms and Ramsey have done some amazing work on allowing Clojure to be built on top of the Unity 3D game engine. There's other tools in the JavaScript land for building game engines also. But why now? Why do we need something else? And it really comes down to the timing of Clojure and ClojureScript. So the appeal of being able to bring the entire toolkit of Clojure and its amazing work with dealing with data and being able to program the way that I want to program games that I'm going to be spending my free time on is a really great time to do it. Because we can also use all of our functional programming techniques to start dealing with some of that complexity, start trying to think of simpler models, and use some of the things we learned from the rest of our Clojure work to apply it to a new domain. And who doesn't like building games or dabbling with games and game programming? So I've found it extremely fun to build. For the past 2.5 years, I've been working on a game and game engine that I've rewritten many, many times. And really the fun has just been building this universe and building on top of it. So let's start with a quick example. And I don't mean to point any fingers or pick on anything related to object-oriented programming. But this kind of showcases a few things of problems that I want to solve. So let's quickly try and digest what's going on here. We have a couple of objects. We have a player object, we have a game object, we have an enemy object. And inside this game, we have a method called run, which is going to run our game. And essentially what we're going to do is iterate over these entities, these objects, and we're going to start manipulating their state. We're going to start calling methods, and quickly notice how we are actually coupling players and enemies together, where both of their states need to be known in order to alter the state of the other. We're also going to handle other things like input, and we're going to end up with an orchestration in our run method where we're going to have lots of different objects that are playing together. So this might be a really great way to start, especially in simple games. It's an obvious place to start. But what happens when we start to add more things in? What happens when the complexity starts to go up? The kinds of games that I'm really interested in tend to be more about content. So think about like Diablo or like Zelda, 2D games that have lots of content and experience by what's in the world and the behaviors that you can actually create. So in that example, we've coupled things together at the code level. And that's one thing that I found to be a little bit difficult, especially when you want to start adding more functionality. And one thing that is kind of obvious to this too with using objects is we've actually intermingled state and the methods that change that state. So that's fundamentally how classes and objects work. but we can change that assumption and separate those two and have a different way of expressing our games more functionally. So what are some ideas that we can now apply to how we might want to express a game? A few things that are on my short list. I want modularity. I want to be able to add new things without breaking other things. I want it to be declarative. And I mean that in the sense of I want to be working on what the game does rather than how it is going to accomplish and do it. So the separation of those two things, I want to say, okay, game engine, you figure out how to run this game. I'm going to tell you all the pieces that you need to account for to express the behaviors that I want, and I want to do it with data. I want it to be functional because I like to be able to test things with data. I can reason about data pretty easily, and I have a lot of tools in Clojure especially to deal with data. I also have a vendetta against global state. I don't like the idea of having a singleton. I don't know who's going to be accessing it, and I want to minimize what all of the functions in my execution strategy are going to have access to at any particular time. And of course, I want to wrap this all up in a nice interactive development environment where I can get instant feedback about the game that I'm creating so it can be more fun. So let's talk more about the modularity aspect of this. So bringing back our object example, we might try to express a game that has, let's say, a space fighting game. We might express it with an object tree that looks a little bit like this. We'll have a hierarchy where, let's say we're trying to create 3 different kinds of missiles. A heat-seeking missile, Sidewinder missile, and then we also decide we want a heat-seeking Sidewinder missile. So how might we go about expressing this in a more of a hierarchical sense? We can take our missile object and we say, okay, a heat-seeking missile is going to inherit the missile object, the Sidewinder missile is going to inherit the missile object, and then as soon as we want that heat-seeking Sidewinder, all of a sudden we're going to start to run into a little bit of trouble. We either need to rewrite our object hierarchy to remove this deadly diamond of death, or we have to deal with the consequences of how we're going to know what methods are actually going to be called, especially if they share the same methods, within this tree. So you can see, imagine if you multiplied this by 100 or 1,000, right, in a content-based game where there are so many different things going on. You can quickly end up with a very rigid structure that's going to take, 1, a ton of planning up front, and 2, that's typically not what happens. You're going to want to change and experiment with the functionality of your game for maximum funness. So this leads us to entity component systems. This is something that's been popularized in about 2007. Dungeon Siege was really the pioneer of this. Scott Billis gave a great talk about it. And basically what we want to do is decouple those really strict hierarchies and think about it more as a collection of aspects, components. So essentially the way we describe things is as a collection of things that it can do, its behaviors. And we want to separate the means for iterating over it from how we describe what the things actually are. So if you do it in this particular way, which lends itself nicely to the games that I want to create that are more related to content, we can easily add, remove, create new things from our existing pool of components without having to deal with really upfront, rigid hierarchies of classes. And I found that it tends to pair really well with functional programming. So what does this look like now if we were trying to describe that same missile Sidewinder, heat-seeking Sidewinder with components? We're going to end up with little buckets. So a heat-seeking missile can move, it can explode, and it can heat-seek. Our Sidewinder missile can move, it can explode, and it can have a sidewinding component. Our heat-seeking Sidewinder is the exact same thing, but it has both the heat-seeking and Sidewinder components. And then, just to cap it off, how might we create new novel things in our game world, like a bomb? It can't move, it's not sidewinding, it's not heat-seeking, it's stationary, it's static. So all it has is the explosive component. So that's all well and good, but how might we express this now in data? So we're going to build up this framework, so to speak, by looking at data and trying to build it off of data first so that we can achieve some of the declarative parts that I really wanted for this type of approach. So here we have an entity. And entity component systems are described in many different ways. Here I'm going to take the most functional way that I have thought of to express it. An entity being a label, so player 1, and a collection of component labels. So notice there's no implementation, there's nothing in here. It's just data. All it's saying is that the entity has those 3 components that it's going to participate in. Next, we have components. And a component is pretty simple. It's a label, and it's a function of component state. So we're introducing a new concept here, component state. And component state belongs to an entity. Okay? So what it's going to do, it's a function, takes component state, returns the next component state. Next, we have a system. A system, like we said before, is in charge of the means of iterating over these entities. So here we are going to say a system is actually just a label. So if we're going to take the movement system, it's a label, it's a function of the overall game state. And it's going to iterate over all of the components, all of the entities that have that particular component. And it's going to be in charge of calling the component function with the component state that for each entity. Right? So each component state belongs to a particular entity. It's iterating over all of them, and it's going to stick them back into the overall game state. So you can think of it as a lens. A system function is a lens to the component function. What we want to do is take wider inputs, pull out just what we need, and then recombine everything at the bottom. Another concept that I want to introduce, which is not often covered, is a scene. A scene is a little bit higher level, where it has a label, but it's also a collection of systems, of system labels. And the reason why that's important is because order of execution is sometimes important. Maybe we need to get input from our controller before we calculate movement. So the order of execution of our system functions can be specified upfront without code. Again, we're using data here to describe how I want the game engine to actually execute the game loop. So what is the pattern here? The key takeaway is if we model it in this way, we're dealing only with data. And if we're dealing with data, we're dealing with values. And we kind of have these new properties that come along with it. So in some ways, you can think of it as kind of this game iconicity. The game is actually data. The data is actually the game, which means at game time, we can alter how the game actually works entirely by declaring different behaviors or changing things. So that allows us to do a lot of things at development time, but also as the game is running. So we've seen how we can describe entities, components, systems, and a scene using this data and functions. But we need something that's actually going to put it all together, right? So what is the actual game? How does it actually run? How do we put it together? So if we were to describe our game state as being a hash map in which we described our entities, our components, our systems, and our scene using data, what we want to do is we want to take all of the system functions out of our game state, and we can do that very easily. By mapping over it in the order in which we defined the scene to be. And we're just going to comp them all together, which is going to return a new function. And it's going to take a single argument, game state. And it's going to return the next game state. So when we talked about state time, remember, it's just different snapshots of state. And we're just going to transform it over time. So this is going to return the next game state. We're going to take the result of that, and we're going to stick it at the top again, and we're going to recur. So essentially, our game loop is a recursive function in which it's getting the instructions of how to execute our game loop from the data itself. So quick summary of what that execution model looks like. We have the game state. It gets passed through a bunch of different system functions until it recurs all over again. If we were just pull out one system, we can see we start with a state. We're going to provide a lens to it. We're going to pull out each entity that's participating in that particular system. We're going to get the next component state for each of those entities. And then we're going to stick it all together again into the game state. Okay? And we're just going to pass it through. So this looks very much like a linear pipeline that we would create in our other Clojure work that we would do in plumbing a bunch of data. So some good things that emerge as a result of this. We've got pure functions. The data itself is a flow of data that's linear. Right? We can see exactly how we specified what's going to happen in what order, and it's predictable. So we can also parallelize this. If there are no dependencies between systems, and each system returns a state, as long as we can separate them without any dependency, we could put those on different threads and combine them again at the bottom if we wanted to get some parallelization. It avoids singletons. The data is actually just in a recursive loop and just being passed in. So we're not having to swap bang in a global state var. Side effects can be isolated. We're building layers of functionality. So if we describe everything in data and then our last system is the rendering system, we've actually prevented a whole bunch of side effects from happening through the rest of our data pipeline until points where we can actually isolate them. It's super dynamic. Components can change their own state only and nothing else. They only have access to what they need. All the benefits, obviously, of immutability. And it's super easy to add new things. In order to add new functionality, we add new systems or new components. And we can express this very declaratively using data. Of course, there are some bad things that come along with anything that we're going to try and do. So, I kind of said, let's minimize what you have access to. If I'm writing a component and I am in charge of returning the next component state, let's say I just have to calculate the next position. Sometimes I'm going to need more than just my last position to tell me where I need to go, right? So this thing that I just showed you kind of breaks down there. How are we going to express that? It's great to keep things really clean and really pure, but at the end of the day, things interact. And that could lead to some bad things like fat components. You guys have heard of things like a God object or a blob object before, where it kind of has knowledge about all of these different things, and it doesn't separate concerns, and it becomes really brittle and hard to change. We didn't talk about performance or polymorphism yet, or tooling. Those are things we're going to have to address too. And one thing for those who are looking at the system functions, they can actually seem really boilerplatey, right? They're parsing a whole bunch of game state, they're pulling out things, they're calling functions, they're recombining it. That sounds like a lot of boilerplate. If I want to add new layers of functionality, I have to go rewrite all of that stuff over and over. So that's something that's not good either. It's not strict at all. It's a data structure, which means it's probably the loosest thing, which means what happens if I accidentally returned nil, right? I forgot to return something. All of a sudden, my game is going to break on the next loop through in unexpected ways. And then we'll talk about tooling too. So we have to settle how we're going to actually share state. Sharing state, as dirty as it is, has to happen because games tend to have things that interact. I can't think of any game where no interaction happens. So we do have to figure that one out. We want to share this stuff without really tightly coupling it. The tightest place you can couple it is in code. Next, we want to make it read-only. We don't want to have anybody arbitrarily changing our state out from underneath us because we're going to end up with really weird bugs as a result. So we want to keep our flow of data in one direction. And we want to minimize what people have access to. So kind of think of it as least privilege of state. So what does coupling look like at the code level? This is a blob component. So if a component is in charge of just giving me the next component state for a particular entity, here, I'm calculating where this thing should be moving to based on collision detection, whether or not they took damage by colliding with an enemy, where they should be positioned and moved to in this frame. And you can see we're mixing a lot of different concerns, and we're ending up in and this is a clear smell here, we're ended up in a nested conditional. So this is going to be really brittle if you want to introduce something else, right? Like, oh, what if there's invincibility? What happens if you don't get hit every single frame? What happens if there's a cooldown? How do I do that now? And you end up bolting things on there, it becomes really, really hard. So let's use some of our knowledge from our other domains in Clojure and say, how might we separate the sender from the receiver to keep it in a single directional flow, but decouple those two things together from each other? Right? So component A and component B, we don't want them to know anything about each other. It shouldn't matter. We do this with conveyance. So we would typically stick an event queue between things. And we could do something similar here. Instead of directly altering each other's state or having to put them all in one component, we can say, here's an event, and here's just an example where we can create kind of this mock messaging system. And I'm going to subscribe to collisions for player one, and I can get the message out. Right? So here, anybody can create a message. Someone's going to have to handle it downstream. So we're pushing that down to the handler rather than to the person who's going to create it. And if we do that, we can now separate those things nicely into separate components. So we can really have a collision component, a movement component, position component, health component. And they're going to be loosely coupled on the message format rather than the implementation of, let's say, a blob component or having to know everything about the entire state of the world in order to do what it needs to do. What might be another solution to this? We can also declare things up front. Just shove this stuff into the system. The system is in charge of how we're going to call component functions. Well, what if I tell it that I'm always going to need player one's position? Okay, maybe I'm an enemy thing, right? And I always just need to know where the player is so I can go hunt them down. If I know I'm always going to need that up front, why don't we just declare that and say, hey, whenever you call this component function, give me this other component state. Okay, so we're pushing that to the game engine. Hey, game engine, you figure out how to run my code. I'm just going to focus on one aspect, which is the component. So how can we continue to make this thing really declarative? In order to make it really, truly declarative, we want to be able to capture what we want to happen all in one place, and we want to be explicit. We want to be able to use our full inventory of all the tools we have to deal with data in Clojure so that we can manipulate the language of our game using Clojure functions. And we want our game engine to interpret this stuff for us, do the right thing for us, and it shouldn't matter how this data gets generated. It doesn't matter where this game spec came from. Our game engine should just figure that out. And for now, we can just avoid macros. We're going to keep it all at data, and that's going to be our DSL. So here's a quick example of what this might look like. A game state function that takes some initial state, in this case a hash map, and we're going to say, here's a bunch of specs. I want you to read those specs. I want you to figure it out. The nice thing about this is we're capturing the essence of what we want the game to be, and letting the game engine figure out how to run it. So if you think about the original example we looked at with objects, we were actually describing all that stuff in one giant run method. So it was all described in code. Here, we're describing it in data, and we're letting the game engine figure out how to actually execute it. So if we were to zoom in on one thing, we can see we've now described the behavior with data instead of code. Here we have an entity called E1, and it has a position on the XY of 20 and 20 on a 2D plane. Right? So we've been able to capture this with data rather than with code or objects, having to construct this ahead of time or in a more rigid fashion with, let's say, objects and hierarchies. How could we interpret this? We can reach right into multi-methods, and we can say, let's just dispatch off of the kind of spec that it is, and we're just going to reduce it. Right? It's just a reducing function. We're going to end up with a hash map. It's going to figure out how to stick this stuff into the game state for us. That shields us from having to know the innards of how the game engine is going to organize our data for us, and we can just focus on specifying our specs. Also, this allows us to now remove some of that boilerplate I talked about before, where maybe there is just a default system that's going to automatically figure out how to call all of your entities with the correct component state so that you can focus on just writing your component. And we can have a new declaration here where we say, I'm going to define a system called S1. It's going to operate on a component called C1 using this component function. Let the game engine figure out how to call that component. I can move on to my next thing. Right? So we've removed a whole bunch of boilerplate as a result of that. So next we have tooling. Last time I checked, things like Unity have really awesome tooling, amazing experience. We've seen how we can do things really nicely close to data, and we have all the environment set up for us in Clojure to do that with data. But there are things that we can get now on top of that, really close to our text editors and to our development environment. One of them is obviously the browser REPL. So the implementation I'm thinking about in the web means that we can connect to our REPL into the browser, evaluate our code, see the results immediately. One thing that always comes up is going to be like, well, if I'm testing this aspect of a game, does that mean now that I have to construct the whole game in order to experiment with this one thing and tweak it? What I found to be a good solution is to use something like dev cards. So dev cards is this little program that lets me visually test things in the browser. So I can create little cards, I can share them with people, and I can view isolated functionality. And it's kind of a mixture between documentation, testing, and a nice visual way of inspecting things. Speaking of inspection, how can we now abuse the properties of the fact that our game state is actually this hash map, it's a data structure, to automatically build the tooling that we want? So here we have just a little GIF of something that I threw together, which is just going to auto-generate a UI for our game state that allows us to inspect it. This is just React. Show us in real time what all the data looks like at any frame, and if we want to manipulate and change it, have it two ways, so that we can alter it and it can change things on the fly. This means while we're playing the game, we can also alter the game. How can you achieve that with something like Clojure? Well, let's just extend our data types. We're going to implement a new protocol, which is going to have a single method called inspect, and it's just going to return a React component. And we're going to recursively evaluate our nested data structure, and we're just going to tell Clojure how to invoke, what to return when we call inspect on it. So we can create recursively a UI now that is our inspector. So really, really nice. And we're just using the fact that we can extend Clojure and its data types to do everything for us. So very little code. We didn't have to specify everything up front. It just figures it out. Because this was a pure function, a recursive function, sometimes you really do want to get things out, right? What happens if you want to monitor frames per second? What happens if you want to be able to inspect that state in your REPL and not just in the visual inspector? Well, one way we can do this is borrow a lesson from Ring and use middleware. So since this is a function and we have access to the game loop as a function, we can just wrap that function as middleware. So here we're going to create a little bit of tooling that's going to allow us to inspect in a read-only way our game state using our REPL. And the way I'm going to achieve that is by specifying an atom that I'm going to copy the latest data into for that frame and make that available. So all it's going to do is take our game loop function, it's going to grab whatever state happened, it's going to stick it into a place that I can inspect it, and return the next function. So we're borrowing a lesson from middleware so you can implement your own tooling very, very simply because you do have access to everything. You can do all the side effects you want at that layer, and it won't matter. Another thing that often comes up when I talk to people about functional and game engines and JavaScript is immediately performance, right? What does performance look like? You know, the games that I'm really interested in are 2D sprite content-based games, so just keep that in mind. But there are a lot of lessons that were learned just by looking at the profiler. Just see what it does. And the fact that you can look at the Clojure and ClojureScript core code means that you can see all the things that it's doing. And the biggest lesson that I got using things like the CPU profiler, the CPU charts to look at the call stack, is that you want to figure out where you're doing lots of work. And rather than trying to make everything faster, try and make your program do less. If you can make your program do less, you will, as a result, go faster. And by being able to view your source code very easily and handy through things like a dev environment, you can actually see when it's going to be doing lots and lots of work. So that kind of led me to a couple of different lessons that I want to pass along in trying to create more of a higher performance game loop. Think about it, 60 times per second we're trying to update this data structure over and over and over in non-trivial ways. One thing that was immediately found, and I'm sure you guys have seen this before, is variadic functions do come with a penalty. It's going to do more work because it needs to dynamically dispatch your code. So in JavaScript terms, in V8, it can't actually optimize it. So it can't create the hidden class to optimize the calling of that particular function. So instead, use multiple arities. You probably already know how you're going to call your function. And if you do, just use multiple arities, right? And specify all of them up front. You'll get the performance boost. V8 can now optimize that, and pretty much every JavaScript engine can do that. Next, partials. Same concept. Has to do more work in order to call your code. So don't use partials. You should know how you're going to call your code, or trying to rearrange it in a way that you can avoid using that. More examples of doing extra work. Empty, pretty innocuous, but it does a lot of things under the covers, if you look at the source, of how it deals with all the different data structures in Clojure and everything that participates in the different abstractions that empty is going to work on. We can also use something that's a little bit simpler, seek, which is going to do the same thing in this case, but avoid extra work for data structures we don't care about. Another great example, keyword equality. Huge performance boost if you just say, instead of using equals, keyword, use keyword identical. It will skip all the extra work that it does, to have, especially with JavaScript, to figure out the whole equality thing, and take a shortcut, make it do less work, therefore higher performance. Runtime polymorphism, you're going to want to avoid multi-methods. Again, it does extra work because it's so dynamic and everything. Instead, my advice in actually trying to implement things in a high-performance way in ClojureScript is you could probably get away with, for a while, with conn to p. Granted, it can't be extended from outside of your code, so you're going to make decisions based on that. As soon as you know more about your problem domain, you might want to actually start implementing def records or def types or protocols, because that is going to be the fastest ways that you can dispatch. Another lesson, this is a contrived example, but if you're going to keep calling the same exact function inside of another function, and it's always going to return that same result, just def it. Right? Skip the extra function calls, don't worry about it, just def it, and then use that def inside of your function instead. Laziness is a thing, obviously, in Clojure. in games and tight loops like this, we don't actually care about laziness. We're not going to deal with infinite sequences. So we don't necessarily want the cost of having to build up lazy sequences and pay for that abstraction. So we want to favor things like reduce over map, maybe loops instead. Don't be ashamed of loop in Clojure, because you can avoid creating all this intermediate stuff, which also has a penalty to pay when it comes to garbage collection. So biggest thing, avoid intermediate collections. There's a lot of tools in Clojure to help avoid this, but it does make a huge difference, because if you think about it, you're going to create a whole bunch of things and just throw them out to build up something procedurally. Then you probably want to rethink what you're doing in that particular function. And in a lot of ways, sometimes just break it out into a loop, create your own accumulator, use transients. If you're isolating that mutable state inside of your function, it doesn't matter. Right? So here, I would also advise just using maybe even a JavaScript array. If you need to bang away at something and accumulate a result, and you're going to do multiple steps to each one of those things, instead of creating those intermediate collections, create a loop, use a transducer, but avoid all of those intermediate collections in a procedural way. Some other ClojureScript specific things. Garbage collection is actually really good. I just want to throw out, just in profiling this implementation that I've been working on, roughly 7 to 10% of your time is going to be spent doing GC. Could that go lower? Sure. Is it right now worth the price of entry? Yes. Does the Google Clojure compiler help in overall frame rate? Immensely. So it's worthwhile to take some of those penalties, but be aware that you are generating more garbage as a result, and JavaScript has to do something about it. JavaScript, Booleans are a mess. If you know something is going to be a Boolean, there is an actual type hint in the ClojureScript compiler to skip all the extra checking. Again, make it do less work. Use arrays and transients when you need to build up intermediate state. And then use the advanced compiler options. Static functions does amazing things. You'll get a solid 30 to 40% speed boost if you implement it in a similar way to what we described by being able to inline the function invocations. Take a quick look at it. It makes a really big difference. And then one thing that people often ask is like, well, is immutability really slow? I've tried to re-implement all this stuff, right, with mutable state and like, oh, I'll just create my own data structure. Typically, it's not that. And you can find a lot more low-hanging fruit. And in the lessons that I've learned, the slowest part is usually something else to do with my implementation and not really functional programming or the Clojure tools that I'm using. So just keep that in mind. There's probably lower-hanging fruit that you should be tackling. And while we have a little bit of time, I just want to show you, what this stuff can look like, just to prove that it actually does stuff. So here we're looking at, this is dev cards, by the way, so kind of mixture of documentation. And so we're just going to mock out a quick little game here. We have some middleware that's running. And I have my player one. We have enemy AI. We have tile maps. We have collision detection. There was 100 game objects on there. And we have attacking, hit points, stuff like that. So if I want to just show how we can move around, we have animations too. And then I'm just going to kill some bunnies. So when we attack them with our fireball, they have hit points and they eventually die. So that's all well and good. But some of the other promises that we have about this was like, well, maybe I should be able to change the behavior of this. So let me go into the state. And this is just auto-generated code. Let me go see what the state is for attacking. For player one, and it has this fireball attack as part of its attack component. And maybe I want to change its damage to 30 hit points. Okay, so now when I attack things, it's going to take 30 hit points away. And maybe I want to increase the speed so it's a lot faster across the game, or I want to make it really, 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 really slow just because I want to fine-tune the experience of it. And I can do this visually, and I can see the representation of that inside of my inspector, and I didn't have to write any of that code at all. So what am I doing with this? I've taken this implementation, and I've been working on something called the Chocolatier. It's kind of a game/game engine about exploration and content, and been able to get this up to 60 frames per second using the advanced optimizations in the Google Clojure compiler, actively in development, and it's really all the things that I want to have when I'm spending my free time in building games. And Lastly, let's continue to push what we believe to be the right way, different tools for tackling games and things that are really complex, using functional paradigms, using Clojure. We have an amazing tool set to do it. And in closing, hopefully you guys have seen how we can apply entity component systems to this problem domain using functional programming, data-oriented, declarative game engines that figure out how to do the things that we want to do it so we can focus on what we want to do. And lastly, speaking in front of you guys has been a dream of mine for starting Clojure 4 years ago. So literally a dream of mine. So thank you for sharing that with me, and hope you guys learned something. Thank you. All right, so we have a few minutes, I believe, for questions. Sure.
Are there certain techniques for doing performance tuning on the Clojure side that work, like the one for VA?
Luckily, in the Java world, there are a ton of tools for doing it, like YourKit and things like that, just to see exactly what's being created from the objects or the classes that are being generated in Java land. So yes, there's good tooling there. Anything related to Java profiling, memory, CPU, et cetera, exists.
But this is strictly for JavaScript.
The main focus, my main focus has been on building this for the web, so targeting the JavaScript environment. As you can see in there, we didn't actually touch anything with rendering. I kind of have a rule not to try and write my own rendering code and let the high-performance libraries that exist for your environment do the work. Yes?
All this stuff is basically just regular DOM objects, right?
So that particular example is using HTML5, using WebGL and then degrading to HTML5 if it doesn't exist. So I'm not actually touching anything other than the canvas, except for the inspector. That is the DOM. That's React. Yes.
Unity has a really cool thing called coroutines. Did you ever think about wanting to use that in Unity?
I'm not sure. I haven't looked at it. What does it do?
Can you repeat those questions?
Oh, sure. So the question was, there's a thing called coroutines in Unity, in the Unity engine. Have I thought about something like that here?
Yeah. So just a quick summary of what it is. It's like a Go loop where you can essentially have a mini event loop where it seems like it's sort of running synchronously, but it's let's say you pause for 1 millisecond and then you repeat. So it's essentially like a Go loop. And I use it a lot to handle things like animations and stuff.
Got it.
Just wanted to-
The way that I've been doing it is I use counters a lot.
Yeah.
And so for animation especially, I'll just keep counters as part of component state to figure out what frame it should be on.
So it's just all bar state.
So it's literally, the entire thing is literally state to state rather than anything that might be non-deterministic in the middle. So for animations and everything, it's literally locked with time. You can change that if you wanted to, but that's how I approached it, just to make it simpler.
How do you handle tick length? How do you make sure it's actually 16 or 60 frames per second? Is that your rendering engine? Or?
So there's, in the web environment, that's request animation frame will match to the refresh rate of your monitor. There are two ways of creating event loops. Game loops. One, which is every single tick is actually the next frame, and there's also fixed time step loops where it will try and call your code, and if it's too slow, it will run your game loop n number of times to catch it up. So the game will run at the same speed, but it will actually be frame skipping in the rendering part of it. So that's two ways of handling it, especially if so in this particular implementation, if it was really dragging, the entire game would move slower. So I don't know if you've experienced that with older games, but the way to solve that is with fixed step time loops too, where you can actually catch it up. Yes?
Look into WebCL for doing stuff like physics or computation.
There's a lot of tooling on the JavaScript side. If you wanted to use physics engines or things like that. In this example for collision detection, I'm actually just bringing in a JavaScript library for R trees to do spatial indexing easier than me having to implement it. All I would recommend is just make sure you isolate and wrap those libraries because they tend to be a lot more stateful in JavaScript. But there are plenty of options for physics too. the challenge might be in wrapping it in a somewhat functional way. Yes?
Have you considered using deforestation as an optimization?
Have I thought about using deforestation as an optimization?
Because you said you would manually remove intermediate data structures. Why don't you have the compiler remove them for you?
That would be awesome. So JavaScript is pretty aggressive in its optimizations to do garbage collection. One thing that I haven't profiled a lot is what the memory is actually doing during the game loop. So I think to your point, there's probably other ways to manage intermediate things that might get generated as a result. Some of them might be opaque to me. It might be implementation details of the language, or in some cases, like the JavaScript the JavaScript engine itself. But I have not taken the step yet in memory land to go figure that stuff out.
Since you're using 70% of your time in garbage collection, that's clearly the heavy thing. As an old whisper, the first thing is memory, right?
Yes. So yes. It is a penalty, and so his point was, if you are spending so much time in GC land, definitely something to take a look at. An old, just a lesson from the Lisp world in making sure you handle memory and everything, so you can be as efficient as possible. Great. Well, thank you so much for your time. Appreciate it.